Welcome students to the first video lecture of EEE or ECE 341 Introduction to Communication Engineering. Before diving into the detailed discussion, let's talk a bit about this course. In this course, we will learn about modulation techniques and the components of a communication systems, etc. This is the gateway to the vast field of communication engineering. The concepts you will learn in this course will be needed to survive the future courses like digital communication, wireless communication, and also mobile networks. So I advise the students to be very attentive to this course. The concepts that are taught in this course are very rich. So without any further ado, let's get started. I have divided the full course into several parts, and this is the first part of our course, which is Introduction to Communication Systems. In this part, we will talk briefly about some of the important components of communication systems, the history of communication systems, and then a little bit about the information theory. And in the final part, we will talk about bandwidth, cable, wireless communication, etc. in a very brief manner. So, what is communication? A vague definition of communication can be transfer of information. Whatever or whenever we transfer information from one place to another, from one person to another, we are actually communicating. What are the mediums of communication? Let's say telephone network, internet, radio and TV broadcasting, wireless mobile communications, Wi-Fi, etc. All are mediums of communications. And we can actually classify communication from different point of views. From one point of view, communication can be divided into two parts: analog communication and digital communication. This is the classification that is of particular importance in this course, because of all other classifications, we will talk about precisely this type of classification of communication throughout this course. We will learn in detail what is analog communication, what is AM, FM, what is digital communication, what are the ways of communicating digitally. So these are the topics we are going to discuss in this course. So moving on, let's talk a bit about history. Right, when we are learning something new, it's customary to talk about the history of it, the development stages of it. So what was the early forms of communication? Before the language was invented, people in the Stone Age used smoke and light for communicating. They used to draw different creatures on the wall of the caves, right? And these are also early mediums of communication. Then when the language is developed, people started using language. And still now, people who are not able to use the language, who are not capable of speaking, they also use sign language. These are shown here with hand gestures, right? Then Mr. Volta invented electric battery, and it's a benchmark in not only in communication engineering, it's a benchmark in all sorts of technological fields, right? Then Professor Joseph Henry was able to ring a bell. Of course, ringing a bell is communication, right? Whenever you go to a friend's house and ring the bell, he gets to know that you are here. This is a medium of communication. Anywhere you are passing some information is actually communication, right? Then comes Morse code. Morse code was used in telegraph. Here is a chart. You can see the different letters and numbers, and their corresponding Morse codes are shown here. So what was done in telegraph was basically a message was converted according to this Morse code chart, and then it was transmitted through the wire line, and in the receiving end, these codes were again directed back to the message. That was the process of telegraph. Imagine you are in 1850s. Then if you wanted to send your friend a message, you couldn't have done it with your Facebook Messenger. You would need this Morse code and telegraph to send this message. Life was difficult back then, right? Then here is some statistics shown. Around 25,000 miles of telegraph wires have been laid across in the US in 1854. It was very costly, so we had to look for new mediums of communication other than telegraph. EM theory was established by James Clerk Maxwell in 1864. 1875 was a landmark. Alexander Graham Bell invented telephone to communicate with her wife. Dedication to wife always pays off, right? Even in the field of engineering. In 1887, Hertz demonstrated physical evidence of EM waves. Then Marconi invented radio in 1900. In 1921, when mobile communication started. Then some other important inventions in the field of communication are given here. You can just take a look. Some of the top telecom manufacturers, you may have heard their names: Cisco, Ericsson, Nokia, etc. So this is one of the important parts of this slide, of this topic. It shows a basic diagram of a communication system. What are the components of it? At first, you need a source of the information. Let's say I am delivering a speech now. This is the source of some information. It may be some music, some pictures, or it may come from a personal computer. So these are the sources of information. These sources of information delivers some message signal. Then the message signal is received by the transmitter. So what is the transmitter? Let me give you a simple example. I am recording a video lecture for my students now. But is it possible that I am talking in my room and my students are listening to it live? Yes, it is possible if I use a radio transmission. But if I am just yelling at the walls, my students will not listen to it in real time sitting in their place, right? It is not possible because the message will lose its strength when it is passed through the air. So it is not possible for my students to listen to me when I am in my room and they are in theirs. So there must be some technique which is used in the radio to transmit my message over a long distance. So that is what transmitter does. Transmitter may be some modulator, it may be some encoding system, maybe it may be some amplifier that converts this message signal into some form which can be transmitted over a long distance, maybe through wired channel, let's say telephone, or maybe wireless, let's say radio. So when the message signal is converted into the transmitted signal by this transmitter signal then goes to the channel. This channel can be wired, as I said, in the case of telephone, or it may be wireless in the case of mobile phone, right? Then the signal transmitted through the channel is received by the receiver. So the receiver is actually the opposite of transmitter. The function of receiver is converting the received signal into the message signal that was earlier sent to the transmitter, and then this message is received by the user of the information. So if I convert the diagram for a radio communication, then it will be something like this. Source of information is the speech or the music played by the radio jockey. Then it goes to the transmitter. Transmitter is actually an FM modulator. You may have heard the word FM, FM 90.4, FM 89.2. These are some popular FM channels of our country. We will talk about it later. Just for time being, let's say this speech of radio jockey is converted through some process with FM modulation technique, and then that is transmitted through the wireless channel, and then your mobile or your radio receives that signal, and then that signal is converted to the music played by the radio jockey in the radio station, and then you can listen to it, right? So this is the whole process of a communication system. These components may vary. The transmitter which is used in the radio communication is not the transmitter used in telephone communication or maybe mobile communication, but the components are basically same. You can use different transmitters, but the function is basically similar. So the three basic elements of a communication system are transmitter, as you have seen, channel, and receiver. I guess I am clear here. We need to measure the information because in engineering measurement is a very important part. Let's look at two examples. First example is, imagine you are sitting in a room looking out the window. You can clearly see that the sun is shining, and at that moment your friend calls you and says that, wow, it's a nice daytime. You will be annoyed with this phone call because you can clearly see that it is a sunny day. Your friend does not need to call you to send this message. So this type of message does not contain any information because you already know that. But let's say your result is published and your friend calls you and says you have got a GPA 4, then it would be a very, very good information bearing message for you, right? Because probability of you getting a GPA 4 is not 100%. There is element of uncertainty. So what we can get out from this is, if the message is very probable, then it contains less information, and if the message is highly improbable, it contains a lot of information. So the information content is inversely proportional with the probability. But this is a very qualitative definition. We have to measure what are the information contents in a message. So we need some parameters to measure the information content. We will talk about it in the next slide. We can measure information in terms of entropy. So what is the definition of entropy? Here is a mathematical definition given here. The entropy of a discrete random variable x is a function of its PMF and is defined by h of x. This is the formula for determining h of x. Now let me explain what x and h of x is. X is a discrete random variable. So what is a discrete random variable? A discrete random variable is such a variable which can attain discrete values according to the outcome of a random event. For example, I am tossing a coin. What can be the outcomes of a coin toss? It can be head or tail. So if my random variable x is actually a random variable corresponding to my coin toss, then let's say if the outcome of my coin toss is head, then we will say that x is equal to 0, and if the outcome of my coin toss is tail, we will say that x is equal to 1. What can be some other examples of random event? Let's say dice. Throwing dice is an example of random event. If I throw a dice and I get 1, then let's say my random variable x is equal to 1. If I get 2, then I will assign the value 2 to my random variable x. That is the functionality of a random variable x. Now hx is the entropy of such a random event. For example, if I consider a case where there may be n outcomes in a random event. If it's a coin toss, then n is equal to 2. If it's throwing a dice, then n is equal to 6. We are generalizing the concept now, and we are considering such a random event where there may be n number of outcomes. And let's say each of these outcomes has certain probability. Now if I again compare it with the coin toss, then there are two outcomes in the coin toss. One is head and the other one is tail. So what is the probability of getting a head? It is 1 by 2 or half. And what is the probability of getting a tail? It is also half. If we consider the example of dice throwing, then the probability of getting 1 is 1 by 6, and every other number 1 to 6, every other number has the same probability, that is 1 by 6. Now if I has a random event where there are number of outcomes are n, and let's say all the probability of all the outcomes may not be same, it may be different. Let's say pi is the probability of ith outcome. If there are total n outcomes, we can actually number them from 1 to n, and let's say I is the general variable, pi is the ith probability of ith outcome. So the total entropy will be summation of the probability of each outcome multiplied by the log of probability of each outcome, and after summing we will take a minus at front. The significance of this minus is that if we know that from the property of log that minus log of x is actually log of 1 by x, so this minus can be absorbed by the log, and the definition can be like this: summation of I equal 1 to n pi log of 1 by pi. So why is this minus necessary, or why is this 1 by pi necessary? We have discussed in the previous slide that if a message is very probable, its information content is very less. So the higher the probability is, so if the pi is high, then 1 by pi is less, and ultimately hx is less. So it is actually referring to the fact that if my probability goes higher, then my information content will go lower, and if my probability goes lower, my information content will be higher. So the unit of hx is bits per sample. We will get a better understanding of this if we look at an example which will be followed. Then moving on, let's consider a binary memoryless source with probabilities p and 1 minus p. Let's say we have an experiment here that has only 2 outcomes. So if a system has only 2 outcomes, then the probability of the outcomes must be 1. If it is a binary system, then the probability of outcomes must be 1. Any of the experiment you do, if there are multiple outcomes, then the probability of all the outcomes must be equal to 1. So if I am considering a binary source, then there are only 2 outcomes, and the sum of the probability of 2 outcomes are always 1. So if I consider the probability of one outcome to be p, then the probability of other outcome must be 1 by p. Let's say coin toss. If I assume that the probability of head is 0.5, then the probability of tail is obviously 1 minus 0.5, which is also 0.5. So if there are only two outcomes, then we will just need to determine the entropy for each of the outcome and then get the sum. So according to the previous formula, there will be I equal to 1 to 2, as there are only two outcomes, and we will need to measure pi into log pi, which is p1 into log p1, and then add with it is p2 into log p2, and then take a minus sign at front. Now in this case, p1 is equal to p and p2 is equal to 1 minus p. So the total hx will be minus p into log p minus 1 minus p into log 1 minus p. I guess this is clear. So if I draw the curve of hx in terms of p, I will get such a curve. So this is the binary entropy, and this is the measure of information actually, and this is the probability p. Now when the probability p is equal to 0, what does that mean? If I have a binary system that has only two outcomes and the probability of one outcome is 0, then it means that the probability of other outcome is 1. That is, it will always the case that we will always get the second outcome. For example, let's say which direction sun can rise, east, west, north or south. We all know that sun rises in the east, right? So the probability of sun rising in the west or probability of the sun rising in the north or south is 0. If it's a binary system and the probability of one outcome is 0, then that means that probability of other outcome will be always 1. That means it's very probable. And as we have discussed earlier, that if event is very probable, then the information content is very less. Now as we are increasing the probability of p, our information will increase, because as the probability goes higher of p, probability of 1 minus p or other event goes lower. It reaches the maximum when the p is 0.5, because it is the most improbable case. If you consider an event in coin toss, then the probability of getting head and tail both are 0.5. So that gives us the most information. And then again p is rather increased, then 1 minus p decreases, and ultimately the information content is for the system is less. So we get a curve like this. Now let's get to the example. A source with bandwidth 4000 Hz is sampled at a Nyquist rate. What is Nyquist rate? Nyquist rate is basically, to be very straightforward and brief, the double of the bandwidth of the signal. So if my signal is 4000 Hz, my Nyquist rate will be 8000. Assuming that the resulting sequence can be approximately modeled by a DMS with alphabet a equal to -2, -1, 0, 1, 2. Okay, that means is here we have a source which can have 5 types of outcomes. They are labeled as -2, -1, 0, 1 and 2. These labels are not necessary. What is necessary is that there are only 5 outcomes. Then these 5 outcomes have probability 1 by 2, 1 by 4, 1 by 8, 1 by 16 and 1 by 16. If you add them, they must be equal to 1. So this means that this source has 5 types of outcomes, and the outcome of the first type, which is -2, is probability of 1 by 2, and this goes on. There are 5 events, 5 outcomes and 5 probabilities. Now we have to determine the rates in bits per second. So at first we will need to determine the information content, or hx, and hx was, if we consider the formula again, hx was minus summation of I equal to 1 to n pi log pi, or summation of pi log 1 by pi from I equal 1 to n. If we consider this formula, then there are only 5 outcomes in this case. So I will be 1 to 5. So we actually need to do is p1 log 1 by p1 plus p2 log 1 by p2, and goes on up to p5 log 1 by p5. That is what is done here. Let's say first event is p1 is this one. So p1 is 1 by 2. Log of 1 by 1 by 2 is 2. Plus p2 is 1 by 4. So 1 by 4 plus log of 1 by 4 is 4. plus P3 is 1 by 8, so 1 by 8 1 by 8 into log of 1 by 1 by 8 is 8, plus then comes P4 and P5. As they have same probability, we can just calculate 1 and then multiply 2 with it. So 1 by 16 is probability of 1 by 4, 1 by 16 into log of 1 by 16, which is log 16, multiplied by 2 because both P4 and P5 have same values. So what we get is 15 by 8, and the unit of Hx was bits per sample. So we are getting 15 by 8 bits per sample, but we have to determine the rate at bits per second. Now Hx is bits per sample, and our sampling rate or Nyquist rate is 8000, the double of this frequency, and the unit is samples per second. So by common sense, if you multiply these two, the unit of Hx is bits per sample, and the unit of the sampling rate, which is the Nyquist rate, 8000 samples per second, the unit is samples per second. Just multiplying these two units will give you bits per second. Bits per sample multiplied by samples per second, so the resulting unit will be bits per second. So the result is 15 by 8 into 8000, which is 15,000 bits per second. So the rate of the source is 15,000 bits per second.